Today we're looking at transformations, and in particular, we're just looking at what are called rigid transformations today. So those would be transformations where the graph that you're looking at, or the shape, this works in geometry as well, um, just moves or gets reflected, but it doesn't change size or shape. So the first one of those is a vertical shift. So if we've got f as a function and c is a positive real number, then the graph of y equals f of x plus c is the graph of y equals f of x shifted c units vertically upward. So if you add a number onto the end of your function, it's going to shift it upward, however many units that is. And if you have y equals f of x minus c, then that's the graph of the f of y equals f of x shifted c units vertically down. So we have a couple of pictures to look at here. This one on the left shows you the blue graph here is exactly like the black graph, but it shifted c units up. And on the second one, the blue graph, exactly the same shape and size as the black graph, but it shifted down. So we have an example here. We've got the graph of y equals f of x down here below. So this is kind of a fun-looking function. And they want us to sketch the graph of y equals f of x minus 2. So the first thing I want to do is talk about what that looks like. Y equals f of x minus 2. That's just a shift vertically down 2 units. Oops. So it's down 2 units. So what I'm going to do on this picture is I'm just going to take each point and I'm going to move it down 2 units just by counting squares on the graph here. So I take this first one and I move down to 1, 2. That would put it here at -4, -5. And then the next one is at 1, 2 right now. If I move it down 2 units, that would put it at -1, 0. And then between those two points were connected by a line segment. So I'm going to connect these 2 points just with a line segment. And it should be perfectly straight, but of course it's hard to draw in here. All right, my next point over here is an open circle. My next good point that I can see. So I'm going to move that one down 2, and I'm going to make that an open circle when I move it down here also, because it's just the exact same thing, just move down 2. Now between the last point that I plotted and this one, there is again a line segment. So I'm just going to connect these two with a line segment here. That's just one line segment. Okay, and then there is another little piece of the graph over here. So there's a piece that's kind of separated from the rest of it. That also needs to be moved down 2 units. So I'm going to take each of the endpoints on this one and move them down 2 units. That would put it here and here. And then connect them with the horizontal line segment that connected them on the original as well. So now if you kind of step back away from the graph a little bit and look at the blue graph in comparison to the red one, you'll see that it looks like it is the same shape and the same size. It's just now in a different location. So now I want you to try the second one that's over here. This one says, given the graph of y equals f of x, which is the same graph we started with last time, sketch the graph of y equals f of x plus 1. So what I want you to do is verbally say how it's going to change, and then make it happen on the graph. I'll pause the video here and complete that and then come back. Okay, welcome back. So verbally, we would say that this moved up 1 unit, vertically upward 1 unit. And then we did that with each of the endpoints that we saw on the original graph here, moved everything vertically upward 1 unit. And so we ended up with a graph that is the same shape and the same size, but now in a different location, changed vertically only. Our next transformation is a horizontal shift. And horizontal means left or right on our graphs. So the function y equals f of x is our black function again here on each of these graphs. And if c is a positive real number, then the graph of y equals f of x plus c is the graph of y equals f of x shifted to the left c units. Now it's important that we look at the difference between this one and the last time we saw f of x plus c. On the previous ones, it said y equals f of x, and then the plus c was outside of the parentheses. So when it's outside of the parentheses, it's actually adding to the y value. That's what it's showing here, which means that that would be a change in y, which is a vertical change on the graph. But this one is showing the f of x plus c, and the plus c part is inside the parentheses. So when you've got something inside the parentheses, it's actually adding to the x. So this is going to be a horizontal change. It's changing the x's. All right, now this one is a little bit hard to remember because if it says f of x plus c, it actually moves to the left c units. And if it says f of x minus c, then it moves to the right c units. Okay, so for our first example over here on the left, we've got another fun looking graph here, and this is going to be the graph of f of x. It says in the information up here, given the graph of y equals f of x, sketch the graph of y equals f of x minus 2. So once again, I want to state verbally what's happening before I go to the graph. So this says x minus 2, it's inside the parentheses, so I know it's changing the x's, not the y's. And it is going to be going to the right 2 units. Let me get a different color now since the graph on this one's starting off on blue, so we'll go to pink. All right, so just like last time, I'm going to take each point from my original function and I'm going to move it 2 units to the right. I'm going to take the endpoint from this segment and the other endpoint from this segment and move it 2 units to the right. And then I just need to connect those with a line segment just like it was on the original function. Then I need to do the same for the other piece of the original function. So I'm going to take this open circle and move it to the right 2 units. And then it'll still be an open circle. And this closed circle to the right 2 units, closed circle, and then connect them. Oops. There we go. So now the new graph again has the same shape and the same size. It's just now shifted horizontally. This one just moved to the right 2 units. So now once again, there's a second example over here, and I want you to try this one. You're going to read it, state verbally which way you think the graph is going to move and how far, and then do it on the graph, and then come back and see how you did. All right, welcome back. So this one you should have stated it's going to move 1 unit to the left because inside the parentheses it says x plus 1. So that is to the left 1 unit. So then we take each of the points from the original function and move them to the left 1 unit, and we end up with a graph that looks exactly the same shape, exactly the same size. It's just shifted in location. Our next transformation is a reflection about the x-axis. So this says that the graph of y equals negative f of x is the same as the graph of y equals f of x, but reflected about the x-axis. So that means your x-axis is acting as a mirror here. So here's the x-axis. And the function that we have to start with over here is actually one of our parent functions that we studied on Friday and practiced today. So this function here is a square root function. Now, if I use this line, the x-axis here, as a mirror, and I flip this graph over that line, reflect it over that line, then I end up with this graph over here. So that's just y equals negative f of x. Now we can do the same thing with this graph here. This one is a little bit more interesting than the one that we had up there, the square root function. So if you like, you can pause at this point and see if you can do this one. See if you can reflect everything from this graph over the x-axis, and then come back and see how you did. If, however, you're not confident with that, then stick with me and I will show you. And at any point, you could always pause the video and try to finish the rest of it. Okay, so I'm going to take each point here and I'm going to reflect it over the x-axis, each point that I can see. So I'm going to start with this open dot here. This one right now is 1 unit above the x-axis. So when I reflect it over the x-axis, it's going to be 1 unit below the x-axis. I'm going to put an open dot right there. Same thing with all the other points that are on this line here. It goes forever to the left with a y value of 1. So every point on this line is 1 unit away from the x-axis. So when I reflect it over, it's going to be 1 unit away from the x-axis, but in the opposite direction. Now I'll do the same thing with the piece of a parabola here. We should talk about our parent functions while we're at it here. This one here would be your constant parent function, a piece of it anyway. This one over here would be your quadratic parent function. All right, so now I'm going to take this piece here, this point, which is, I guess, a starting point or an ending point, depending how you look at it, of the parabola. And right now it is 2 units away from the x-axis. So when I reflect it over the x-axis, it's going to be 2 units away in the other direction. Now this whole picture is supposed to flip over, and that's the only clear point that they gave me where they actually plotted a point. However, that doesn't mean that other points don't exist on this picture. Like this point right here, I could use to help me make sure I get a better picture. This point right now is 3 units away from the x-axis, below it. So when I reflect it over the x-axis, it would be 3 units above the x-axis. So it'd be right there. I could do that again with this point. This point is 2 units away from the x-axis. So when I reflect it over the x-axis, it'll be 2 units away on the other side. And that kind of gives me a little more to make sure that I get the right shape here. I could do another one if I want to, like maybe this point right here. I reflect this one over the x-axis. Right now it is 1 unit up. So it would be 1 unit down when it's reflected. And that gives me enough to really get a decent picture here. So I'm going to go ahead and sketch in my parabola. Oops. Well, that's kind of cool. I'm going to use that in the future. Okay, there we go. So now the new picture actually has the same shape and the same size, but now it is a reflection of the original one. And the line of reflection is the x-axis on this one. Our final transformation is a reflection about the y-axis. And so this one says the graph of y equals f of negative x is the same as the graph of y equals f of x, but reflected about the y-axis. So again, the negative on this one is in a different location. It's inside the parentheses, so it's with the x. So really, this one is saying that the x values are going to change, but the y values are not. So again, I've got my square root parent function here because this is a good one to use for reflections. If I reflect it over the y-axis, this would be my line of reflection here. Then flipping it over the y-axis would give me this picture. So each of the points that are over here are going to be the same distance away from the y-axis, but in the opposite direction. So here, this one would be here. Go 4 units away, and so on. So it would create the same picture, same shape, same size, but just flipped over the y-axis. Okay, so we've got our same little fun graph here, and you should flip this one over the y-axis. You're going to do that by taking each point and moving it an equal distance across the y-axis from however far from the y-axis it is right now. This would be a good place to pause the video and try this one and see how you do. Okay, so when you reflect it over the y-axis, this piece that's pointing left will now be pointing right. Just like if you were pointing in a mirror, it kind of looks like the mirror is pointing back at you. And the parabola piece of it just is going the other way. So actually, if you put these two together, they end up making the full parabola there, only because the vertex of that parabola was on the y-axis.